Understanding search algorithm efficiency in practical applications in today's digital landscape. Search algorithms form the backbone of efficient data retrieval across industries ranging from e-commerce platforms to scientific research databases. These specialized procedures enable systems to quickly locate information within vast datasets by employing distinct methodologies tailored for different problem spaces. The performance characteristics of these algorithms determine their applicability in real-world scenarios where speed and resource optimization are critical factors. By analyzing time complexity metrics such as Big O notation, developers can make informed decisions when selecting appropriate search techniques for particular applications. Foundational concepts in data searching involve systematically locating elements within structured collections through predefined rules and operations. The effectiveness of any search method depends largely on how well its approach aligns with the dataset's organization and access patterns. Two primary categories define modern search paradigms: sequential searches that examine each element linearly, and divide and conquer strategies that partition data sets strategically before examining subsets recursively. Understanding these fundamental distinctions helps programmers choose optimal solutions based on input size and structure. Linear search remains one of the simplest approaches but demonstrates poor scalability due to its O(n) time complexity. This means processing times increase proportionally with larger datasets, making it unsuitable for extensive collections where efficiency is paramount. Better alternatives exist for sorted arrays using binary search, which reduces average case performance significantly by having the search space at every iteration. However, maintaining sorted order requires additional overhead during insertions and deletions. Time complexity comparison: linear search has an upper bound of O(n), while binary search operates efficiently with O log n complexity. Use cases: binary search excels with static sorted datasets, whereas linear search works better for unsorted lists requiring frequent updates. Both methods have inherent trade-offs between simplicity and performance. Choosing between them often comes down to balancing implementation ease against expected query frequency and dataset size constraints. Advanced techniques beyond basic models: as computational needs evolve, more sophisticated search mechanisms emerge to address complex querying requirements beyond basic pattern matching. These advanced approaches incorporate probabilistic models and heuristic-based optimizations. Hashing provides constant time lookup capabilities by mapping keys to fixed size values using mathematical functions. When implemented correctly, hash tables allow near-instantaneous data access regardless of collection size. Caching strategies further enhance search performance by storing frequently accessed items in memory locations closer to execution contexts. This reduces disk I/O operations and minimizes latency for common queries. Distributed computing frameworks employ parallelization techniques to process massive datasets across multiple nodes simultaneously. MapReduce architectures exemplify this concept by dividing tasks among clusters and aggregating results efficiently. Machine learning integration represents another frontier in smart search technologies. Predictive analytics can anticipate user intent and prioritize relevant results automatically without explicit keyword matches. Evaluating modern search frameworks: current industry benchmarks show significant improvements in search engine response times thanks to innovations in indexing strategies and query parsing techniques. Leading search engines now achieve sub-millisecond latencies for most standard requests. Recent studies indicate that hybrid approaches combining traditional indexing with neural network components yield superior accuracy rates compared to purely rule-based systems. Alone. These integrated models adapt dynamically to changing usage patterns over time. Memory management plays a crucial role in maintaining high throughput levels under heavy load conditions. Efficient garbage collection implementations prevent excessive overhead from accumulating in used objects unnecessarily. Monitoring tools help identify bottlenecks by tracking key performance indicators like cache hit ratios and query distribution patterns. Proactive tuning based on these metrics ensures sustained optimal operation even during peak traffic periods. Algorithmic variants and their characteristics variations arise naturally depending on specific application domains and data structures involved. Some variants optimize for worst-case scenarios while others focus on minimizing average-case delays. Tree structures excel at prefix-based searches commonly used in auto-completion features found in many web interfaces. They store characters along tree branches, allowing rapid traversal through possible word formations. Binary indexed trees offer efficient range, some queries useful in financial modeling and statistical analysis applications. Their logarithmic update/query complexities make them suitable for dynamic datasets requiring frequent modifications. Segment trees provide flexible interval manipulation capabilities ideal for problems involving range minimum/maximum queries or other similar spatial operations. Radix sort leverages digit-by-digit comparisons rather than pairwise element swaps typical in comparison sorts. Its stability makes it particularly effective for sorting strings or numbers with uniform lengths. Bloom filters utilize probabilistic membership testing with minimal storage footprints. While they occasionally produce false positives, their ability to rapidly eliminate non-members makes them invaluable in pre-filtering stages before more rigorous checks occur. Performance optimization strategies. Optimizing search algorithms involves careful consideration of various factors including hardware limitations, memory availability, and concurrency requirements. Proper profiling identifies areas needing improvement effectively. Pipelining techniques break down search processes into smaller units processed concurrently whenever feasible. This maximizes utilization of available resources and reduces idle waiting times. Vectorization allows simultaneous computation across entire arrays instead of individual elements sequentially. Modern processors support single instruction multiple data (SIMD) extensions facilitating this optimization path. Branch prediction heuristics aim to minimize pipeline stalls caused by conditional instructions. Accurate predictions maintain smooth execution flow, preventing unnecessary flushes and restarts. Code restructuring eliminates redundant calculations and reorganizes logic sequences for improved cache locality. This leads to reduced memory accesses, improving overall system responsiveness. Pre-computing certain aspects ahead of runtime enables faster query responses by eliminating need for repeated expensive computations during actual search phases. Implementation challenges and considerations. Designing robust search systems presents numerous challenges related to consistency, reliability, and fault tolerance across distributed environments. Ensuring correct behavior despite potential failures requires thoughtful architecture choices. Consistency models dictate how updates propagate through networks, affecting perceived state visibility. Strong consistency guarantees precise synchronization but may introduce latency penalties during write operations. Reliability mechanisms involve replication strategies, ensuring continued service availability even when partial infrastructure fails unexpectedly. Redundancy increases resilience against component malfunctions. Fault tolerance incorporates error detection and recovery protocols, enabling uninterrupted operation following transient issues. Checkpointing procedures facilitate restoration points for failed transactions. Security considerations include encryption protocols protecting sensitive information both at rest and in transit. Access control policies restrict unauthorized retrievals, preserving data integrity. Scalability dimensions must account for horizontal scaling possibilities, expanding capacity without compromising existing functionality seamlessly. Load balancing distributes incoming requests evenly, preventing hotspots forming. Evolving trends in search technology. Ongoing advancements continue shaping the future direction of search technology development. Emerging trends suggest increasing emphasis on contextual understanding and adaptive learning capabilities. Natural language processing enhancements enable deeper semantic interpretations beyond simple keyword matching. Contextual embeddings capture relationships between terms, improving relevance assessments. Federated search architectures allow querying across decentralized sources, maintaining privacy by keeping data localized. This addresses growing concerns around centralized data repositories exposing personal information risks. Quantum computing promises revolutionary changes, potentially solving currently intractable search problems exponentially faster. Though still experimental, early prototypes demonstrate promising theoretical advantages. Edge computing deployment shifts processing closer to end users, reducing transmission delays. This improves interactive experiences where immediate feedback is essential. Sustainable design principles guide energy-efficient implementations considering environmental impact alongside technical specifications. Power-aware scheduling optimizes consumption profiles intelligently. Comparative analysis of popular methods and objective evaluation comparing leading search techniques reveals distinct strengths and weaknesses influencing suitability for different use cases. Criteria considered include time complexity, memory footprint, and adaptability features. Binary search outperforms linear counterparts significantly in ordered collections with predictable access patterns. Its logarithmic growth rate becomes increasingly advantageous as dataset sizes expand. Hash tables deliver exceptional lookup speeds at the expense of higher memory requirements. Collisions necessitate additional handling mechanisms impacting practical effectiveness. Tries maintain efficiency for prefix-based queries but consume considerable memory proportional to the number of stored entries. Performance degrades noticeably with very large dictionaries containing millions of items. Bloom filters excel in space-constrained situations, providing quick elimination of irrelevant candidates though accepting some level of uncertainty regarding outcomes. Each technique balances competing priorities according to specific operational demands, creating diverse options available to practitioners. Practical application scenarios. Real-world examples illustrate how abstract concepts translate into tangible benefits across various sectors. E-commerce platforms benefit immensely from optimized product discovery mechanisms, enhancing customer satisfaction. Healthcare institutions leverage advanced medical record search systems, accelerating diagnosis timelines through rapid information retrieval from patient histories. Scientific researchers utilize powerful database query engines, accessing vast genomic datasets, contributing to breakthrough discoveries in genetics and biotechnology fields. Financial services companies implement fraud detection systems relying on anomaly identification via sophisticated pattern recognition algorithms operating in real time. Gaming studios integrate procedural generation techniques combined with intelligent search routines, producing immersive virtual worlds populated dynamically according to player interactions. Transportation networks apply route optimization algorithms, calculating shortest paths through graph representations, supporting logistics planning and navigation assistance services globally. Future directions and research opportunities. Continued innovation drives ongoing exploration into novel search methodologies, addressing current limitations while unlocking new possibilities. Several active research avenues promise transformative impacts across disciplines. Self-adjusting data structures dynamically modify themselves based on observed access patterns, optimizing long-term performance proactively rather than reactively adjusting after the fact. Fully homomorphic encryption enables encrypted computations, preserving confidentiality throughout entire processing pipelines, opening doors for secure collaborative environments sharing sensitive knowledge safely. Multidimensional indexing schemes handle complex queries spanning multiple attributes simultaneously, offering richer analytical perspectives previously unavailable through simpler constructs. Interactive machine teaching introduces human-in-the-loop refinement cycles, improving model quality iteratively through targeted example corrections, guiding AI assistants toward desired behaviors. Cross-disciplinary collaborations foster unexpected synergies, merging domain-specific expertise with general-purpose algorithmic foundations, producing holistic solutions tackling multifaceted challenges effectively. Conclusion: this examination of search algorithms underscores their foundational role in contemporary computing landscapes. Effective implementation hinges upon thorough comprehension of underlying principles governing performance characteristics and application appropriateness. By critically evaluating alternative approaches and staying abreast of emerging developments, Professionals can strategically select or develop solutions meeting evolving business requirements while maximizing resource utilization efficiencies sustainably.